Today's topic is circular motion. Initially, all students are taught that acceleration centripetal acts towards the center, while instantaneous velocity acts tangent to the circle. To some, this seems a bit odd, so hopefully, with some common arguments, I can convince the skeptics that this is the case and it becomes a little bit easier to remember. At this point, I should probably admit that I'm an older brother that loved to torture his younger brothers. The problem was that you didn't want to hurt them. So, one method of inflicting some kind of pain was to take a sock, shove it down to the bottom of another sock, and kind of ball it up. If you spun this over your head, you could get it going pretty fast, and then you could launch it at your brother. The problem is, while it's spinning over your head, when do you release it? This is a problem because you get one shot at this. So do you release it when it's in front of your head, or do you release it when it's to the side of your head? You should be picking to the side of your head, because once you let go of the sock in your hand, the balled up sock that's going in a circle will end up traveling straight. So if you release it at the side of your head, you stand a great chance of hitting your brother, which should be a lot of fun. Basically, in conclusion, the velocity at any instant is tangent to the circle that the object is forced to be in. If you remove this force, then your object travels in a straight line. So, now the acceleration centripetal part. We're going to do this using a Coke from McDonald's and a Batmobile. I know. It's an ugly Batmobile, but it's the best I could do. Okay, so how are we going to use a Coke and a Batmobile to prove acceleration centripetal acts towards the center of the circle? Well, first, when you're picking up your Coke and you're at the drive-thru and your velocity is 0, what does the Coke look like? Well, it looks flat. In other words, the top of it, the surface of the Coke, is horizontal. Fair enough? Now, leaving the drive-thru, as you accelerate away from the drive-thru, what happens to the Coke? Well, it sloshes backwards. What does that mean? Well, I know the Batmobile is accelerating forward, but the pop is sloshing backwards. Fair enough. Once we get onto the highway, and we're traveling at 100 kilometers, what does the pop look like? Well, it's horizontal, or it's not sloshing at all. It has a nice level surface. Fair enough. What happens if we have to brake hard? Well, if we have to brake hard and incur a negative acceleration, then the pop sloshes forward. Fair enough. Pop sloshes forward, negative acceleration. A little review. There's two ways to have a negative acceleration. In this situation, a negative acceleration is us slowing down in the positive direction. Fair enough. Both of these methods, though, are easily seen from a velocity time graph, which is probably the easiest way to explain how negative and positive accelerations work. In summary, constant velocities typically have horizontal, flat, or horizontal surfaces at the top of our pop. Accelerating. If it sloshes backwards, that means we're accelerating forwards. If it sloshes forwards, that means we're accelerating backwards. So, if you're in a non-accelerating frame of reference, you don't have any sloshing. If you're in an accelerating frame of reference, whatever way it sloshes, the acceleration's in the opposite direction. Okay, so now we're going to go and take the Batmobile to a traffic circle. If you're driving around the Batmobile in a traffic circle with a large Coke from McDonald's, what you'll notice is that the Coke typically builds up on the outside of the curve. In other words, it sloshes to the outside. Well, what does that mean to us? That means that the acceleration is acting towards the center. So, doesn't matter where you look at it on the circle, the pop is sloshing to the outside, the acceleration is acting to the center. Therefore, we know that the acceleration centripetal acts towards the center of a circle because the pop doesn't lie. Now, there is another method of doing this that I like to show my kids, and that's basically using vector subtraction. Vector subtraction is a little rare because we're used to doing vector addition using vector arrows. You know, the whole tip to tail thing. Anyway, the formula for acceleration is delta v over delta t. The delta basically tells us that we should be going velocity final minus velocity initial over our change in time. Well, what is Vf and Vi? Vf and Vi are two instantaneous velocities. Fair enough. In other words, they're two tangents to the circle. Okay, now this formula wants me to go Vf minus Vi. I don't know how to minus Vi. So what am I going to do? I'm going to add a negative Vi. Basically the same thing. Negative Vi is basically the same magnitude, just the opposite direction. So how do we add vectors again? Well, it's tip to tail. So I'm going to take my Vf and I'm going to add my negative Vi to it, and then draw my resultant, which goes from the very beginning to the very end. And if you look at the little blue line with the double arrowhead, my resultant, you'll notice that it's now pointing towards the center. I must admit, this is not exactly 100% true with these vector arrows, but it's pretty darn close. Centrifugal force versus centripetal force. A lot of teachers don't teach centrifugal force. Why? Because it is not the force acting on the object that's going in the circle. Matter of fact, it is our object that's going in a circle acting on some other object. Now, I used to like this centrifugal force. Why would I like it? Well, not as teaching it, but as going back to me being an older brother, I used to love when I was on the inside of the... Well, my brothers and I were in the backseat of the car. Dad freshly arm-rolled it, and we'd go in a circle, and I would notice that I was on the inside of the curve. I would get a grin on my face, and my brothers would start to shake with fear. Why? Because they knew they were going to get squished into the side of the car. Why does that happen? Why do I get to exert more force than them? Well, simply because my body wants to travel in a straight line. To make me go in a curve requires friction from the car seat. Because it was arm-rolled, there was no friction. My brother's not so lucky. He has a door that's keeping him in a circle, that keeps pushing him towards the center. So he's going to have a curved path where I'm going to have a straighter path. And what that means is that our paths will eventually cross. When they cross, that means I'm meeting him. Now, I, in the red, basically am going to be pushing on him. That is the force centrifugal. The force that he exerts on me will actually become my centripetal force, because once I collide with him, I will stop traveling straight and actually end up back in a circle again with a slightly larger radius. At this point, he's squished like a bug. Kind of fun times. Anyway, I hope you enjoyed it. That's all. Thanks.